This is the model of grid connected PV system with nonlinear load along with the double tuned filter. Okay. So this model consists of PV panel and then boost converter and then inverter, and then here we have grid, here we have nonlinear load, and here we have double tuned filter. So here you can see that the boost converter, right? This boost converter going to be controlled by means of MPPT algorithm. So here we are using MPPT, P into MPPT. So that P into MPPT going to receive two inputs. So one is PV voltage and current. So based upon PV voltage and current, it's going to be decide the duty cycle. Okay. So this duty cycle going to be processed via this PWM generator. So this PWM generator going to be generate the pulse per this IGBT in order to extract the maximum power from the PV panel. So here we are having PV panel, that means PV array, right? So I'm going to click this plot button. So you can see here, right? So we are generating the maximum power around 3.048 megawatt. Okay, so it can generate maximum power of 3 megawatt. So here we are measuring the PV voltage and current. So inside that MPPT algorithm, so here you can see that, right? So we are measuring voltage and current of PV, and then here we are consider initial duty cycle equal to 0.42, the maximum duty cycle equal to 0.9, and minimum duty cycle equal to 0.1, and change in duty cycle will be 0.008. Okay, and then in order to implement that P into MPPT, so you have to fix three more parameter, nothing but V volt, P volt, and D volt. Here reference volt, nothing but the previous instant voltage, power, and duty cycle. So initially it does not have any value for V volt, P volt, and D reference volt. So here we are fixing values for V volt, P volt, and D reference volt. And then here you can see that we are calculating the power of the PV by multiplying voltage and current. So here we are calculating the voltage, change in voltage and change in power. Okay. So based upon a condition, change in power and change in voltage, so you need to increment the duty cycle. So here you can see that when change in power is greater than 0, and then here you have to check the change in voltage. If change in voltage is greater than 0, you need to decrement the duty cycle in order to bring back that that means we are going to extract the maximum power at peak point. If suppose change in voltage is not greater than 0, we need to increment the duty cycle in order to extract the maximum power. Okay, so based upon this condition, based upon change in power and change in voltage, so here we need to increment or decrement the duty cycle. And then if suppose if change in power equal to 0, so no need to do any changes in the duty cycle. So you have to keep T reference equal to D reference volt, and then you have to check the D reference value calculated from these conditions, right? So whether it is within minimum maximum limit. If it is within maximum minimum limit, no problem. If suppose that means if it not obey this condition, then you have to make condition D reference equal to D reference volt. So you have to maintain previous duty cycle. Okay. So here we are overwriting the current duty cycle power and voltage with the previous duty cycle power and voltage. So this code will be keep on executing in order to get the maximum power from the PV panel. So and then here you can see that the boost converter L C value, right? So the L and C value is going to be designed based upon the PV power and DC voltage requirement and the input voltage, right? So already I told you that PV power is around 3.0448 megawatt, and then here you can see that the voltage will be around 319 volt, right? So the terminal voltage at 1000 watts per meter square, which is equal to 319. So here the voltage will be maintained at 319. So here I am going to fix the DC link voltage equal to 600 volt. Okay, so here 319 volt So 319, and then so here 600, and then the power of the PV array is 3.048 megawatt or 3 megawatt. So based upon this condition, you have to decide the value of boost converter, right? So this is the equation used for calculating the LNC value for the boost converter. Okay, so this is an equation. So here you can see that power of PV array is the terminal voltage of the PV, and then switching frequency of the boost converter. This is a dieseling voltage of the, that means output voltage of the boost converter, and then these are the equation used for calculating LNC. That means IOT max, ripple inductor current, ripple capacitor voltage. Okay, so once you execute, you will see that value of LNC. Okay, so that LNC value you can use here, right? So you can use that LNC value here. Okay, so this is a part of the PV and boost converter along with the MPPT algorithm. So next to move on to inverter. So here we have inverter connected with the output of the boost converter. Okay, so this inverter going to be controlled by means of decay control concept. Okay, so for that we need two control loop. One is voltage control loop. So this is voltage control loop. Another one is this is current control loop. Okay, so the voltage control loop, right? So why we are using voltage control loop means we need to maintain the voltage here is around 600, right? 600 volt. So we need to maintain 600 volt here. So for that we need a voltage control loop. So here we are measuring the DC link voltage and compare with reference voltage, and then it's going to be converted into per unit, and then it's going to be processed via PID controller, right? So this will be provide the reference current. So reference current is known as ID reference. Okay, so this is ID reference. So here we are going to send only real power, so we are not sending any reactive power, so IP reference will be 0. So that's why there is no connection in this port, right? And then here we are going to measure the current, right? Here we are going to measure the current. So this is IG. Okay, and then it's going to be converted into per unit. So after that you have to convert that quantity. Actually here we have ABC quantity, right? So that ABC quantity converted into dq naught by using Park transformation. So here we are using Park transformation for converting ABC to dq naught, and then here we are going to control only two parameter, only ID reference and another so ID and IQ. So we are taking only ID and IQ. Okay, so this is ID. So this is IQ. Okay, so this is ID reference and IQ reference. So both are will be compared here, right? So that is called DQ current control concept. Okay, so after comparing that current, so error current will be processed by a PID controller. So this will be generate the control signal, okay, in the form of D and Q. So next we have to convert DQ naught to ABC by using inverse Park transformation, and then it going to be processed via PWM generator, sinusoidal PWM generator. Okay, so this is sinusoidal PWM generator, and then it will be generate the pulse. Okay, so this pulse going to be control this inverter in order to send the power from the PV to this point of common coupling. Okay, so this is the inverter controlling the grid connected PV system. Okay, so whatever power generating from the PV, so that will be sent to the this point of common coupling. So this is a point of common coupling. So in point of common coupling we are connected grid, nonlinear load, and then double tuned to filter. Okay, and then so here you can see that, so here we are measuring the PV voltage. So this is used for measuring the PV voltage, current, and power, and this is used for measuring the grid voltage, grid current, and then inverter voltage, inverter current, and then this is used for measuring the load voltage, load current. This is double tuned filter voltage and double tuned filter current. Okay, so first time I am going to explain the result without the double tuned filter. So here I am going to comment out this one. So here I am going to comment out this one, and then I am going to explain the result of this system without double tuned filter. Okay, so here I'm going to simulate this model, and then I'm going to show the results. Okay, so this is the result we are getting for a grid connected PV system along with the nonlinear load without considering the double tuned filter. So here you can see that, so we are getting around voltage around 310 or 319 volt, and then we are getting around 10,000 amps, and then so the PV power around 3 megawatt. Okay, so here we are generating 3 megawatt power. Okay, and then here you can see that the grid voltage is sinusoidal, and then you can see the grid current having distorted waveform. Okay, so this is the inverter voltage, and then this is the inverter current, and here you can see that, so this is the load voltage, so this is the load current. You can see that load current is not non-sinusoidal, right? Because of non-linear load is non-sinusoidal, and then this is a double tuned filter. That means this point we are not connected double tuned filter, so you can see that current will be zero. So current is zero. Okay, and then here you can see that, so because of this non-linear load, the current will be non-sinusoidal. So because of this, it is going to affect this grid current. Okay, so grid current quality going to be affected in the system. So this is result because of that nonlinear load. So I will explain here. I'm going to take out nonlinear load, because so we need to explain without considering any load in the system. Okay, so now I'm going to not considering any load, and also I'm not considering double tuned filter. So now I'm going to simulate this model. So here there is no load. Okay, so then the load current and the double tuned filter, that will be zero, because we are not using that nonlinear load and the double tuned filter. So we are having only so here we are having only the main grid, right? So whatever power we are generating, right, so that will be sent to the grid. Okay, so already I simulate this model, so again I am going to simulate this one. So we have only PV, boost converter, inverter, and is going to be connected to the grid. So whatever power we are generating from that PV, right, so that going to be sent to the grid. Okay, it is not going to be shared with any load. Okay, so this is the result we are getting, right? So now we can see that we are getting almost the sinusoidal grid current, right? Because we are not using any non-linear load. Okay, and also I will show the THT of the grid current. Okay, then only you can understand the concept better. So now it is simulated, right? So after simulation, the result will be stored here, output, right? So just you go to track this scope data. So just you go to click this one, and then here you can see the scope data, track this one, and then enter here. So next you go to open the continuous, and then go to tools, and then go to effect analysis, and then here you can take the second input known as a grid current, right? In this scope, right? Just use second input, and then change to same as maximum frequency and net display. Okay, so now we can see that, so the TST of the current, right, the current is around 4.65%, so less than 5% in only. Okay, here we are not using any nonlinear load or tuned filter. So whatever power we are generating, if we are giving to that grid, so the grid current having around 4.65% TST. Okay, the same system. So now I'm going to add this nonlinear load, right? Now I'm adding this nonlinear load. I'm going to simulate this model, and then you have to check the results. Now you can see the result of the PV voltage, current and power, and then grid voltage, current, and then inverter voltage and current. So this is load voltage and load current. This is double duty filter voltage, but here we are not used double duty filter now. Okay, now we can see that the grid current quality, right, is having some distortion, right? This is not smooth, right? So this is because of this the nonlinear nature of that load. Okay, so this is because of that nonlinear load of this uh, system. Okay, now I'm going to check the result. Okay, so again I'm going to go to output and then click scope data and enter, and then again I'm going to command window, then again I'm going to continuous and go to tools, go to FFT analysis, and then refresh, and then click input 2. Now I'm going to change same as the maximum frequency and then check the detail. Now we can see that the THD, right? So THD is 7.81. When we are not using nonlinear load, right? So we are getting only 4.81% THD, right? So that means is less than 5% only. So when we are feeding the water power we are generating from the PV to the grid, so the current THD of the grid current will be 7.87. But now we are adding that nonlinear load in the system. Because of the nonlinear load, so THD is around 7.87%, is more than 5%. It is not accepted in this system. So not to overcome that, we not to reduce the THD in the grid current, right? So now I'm going to use double tuned filter. So here you can see that the list, you can click the display. So here you will see that the fifth order and the seventh order having highest harmonic percentage. So I'm going to use double tuned filter to tune the fifth and the seventh harmonic. So here I'm going to use double tuned filter. So this is a double tuned filter. Okay. So here I'm going to use and I'm going to tune the tuning frequency. I'm going to consider as fifth and seventh order. Okay. So these are the rating of this the W20 filter. So you have to take 400 volt 50 hertz and then 4 megawatt. Okay, and then here based upon this grid voltage, grid and the grid frequency, you have to select this one. Okay, so now I'm going to simulate this model, same model with that means this model have nonlinear load, and now I added the W20 filter. So now I'm going to simulate this model. So now we can see that the grid current will be have sinusoidal, almost sinusoidal. Okay, and also because of this nonlinear load, right, that problem will be overcome by means of this double tuned filter. Okay, so it have some sinusoidal nature current, right? So we would wait for a completion of simulation, and then after that we have to check the THD. Okay, when compared to previous scenario, right, without considering a double tuned filter, the current quality, grid current quality, right? So this one, right? So it's not a sinusoidal, yeah, it have some distorted wave. Now we added this double tuned filter. Because of that, it have some smooth sinusoidal waveform. So now I'm going to check the THD. So here again I'm going to track the scope data and enter, and then I'm going to command continuous tools FFT and click refresh, and then click input 2, and then change to same as maximum frequency and display. So now you can see that the THD, right? The THD is 4.57%. Okay, so when we are using nonlinear load, right? So without considering double tuned filter, we are getting around 7.87%. Okay, so now we added this double tuned filter. So because of double tuned filter, the THD is now is 4.57%. So is less than 5% only. Okay, so we reduce the THD by means of this double tuned filter. Okay, this is the working of this model. Okay, thank you so much. Bye bye.